Hey everyone, my name is Qingqing Mao, and I currently work for Dascena as the head of data science and engineering. And my previously I worked for Primary AI as a senior staff data scientist there. And today I'm actually gonna talk about building scalable natural language processing pipelines with Ray. And I recently have this affiliation change, but many of the content in this talk were actually based on my previous work at Primary AI, just to mention that. And I'm gonna start with some very general ideas about how people think about data science. And I think, everyone talks about this and many people know about this, and many people also know like what's the problem with that, right? So in an ideal world, a lot of times you think about data scientists are the ones that actually, do the exploratory analysis and train the model and do a lot of testing and data cleaning and all these things. And then at the end, you deliver a model, right? So that's your deliverable. And you give the model to the engineers, and engineers are the ones that care about whatever runtime environment there it is, and also care about the scaling and all these issues there. So this works well for well-defined machine learning problems. For example, if it's a classifier that you take a given input and then you just output a yes or no label, and that's okay. And the data scientists can just do their job, and then they just give the model to the engineers, and they don't really need to worry much about scaling and all these things. And they can use the standard tools to actually train the model, right? So TensorFlow and PyTorch, and many of these actually have distributed computing features in it. So you can actually train it in a distributed way, and you don't need to worry too much. And data scientist's job is really just make sure you prepare the data and get the label right, all the labels right, and then do your standard procedure there. But that's actually not what happens in practice for a more complex problem. So in practice, a lot of times your task may not actually have a very clear boundary and fixed input and output. I can explain a little bit more later when I talk about these NLP pipelines. And it's also often when a lot of people just talking about machine learning applications, and it feels like everything can be simply just done in a single machine learning model, but that's never true. And in the real world, a lot of times you're actually facing things that you need to combine rule-based models with machine learning approaches together to get into a hybrid approach. This actually also, in natural language processing, all time people actually joke about all the AI are just regular expressions. And this is still actually partially true in natural language processing. A lot of times you actually need to, use some regex to do some initial filtering and some of the cleanup. And then after that, you can probably, later steps can have a machine learning model in it to actually significantly improve your result. And this actually raised a question because there can be subtle dependencies between different tasks. Because if your pipeline is relatively long, and you may have some pre-filtering and all these tasks, and the awesome like rule-based systems, and some of these can actually affect the later machine learning model performance, and it will all affect the overall result you can get from this computation pipeline. And I'll give an example in this natural language processing. This is super simple, like kind of like a very abstract one. So you have a text corpus that you need to do some analysis on. And you send it in, and there are some standard pre-processing on these things that includes, text cleaning and removing these weird characters and punctuation and segmentation and tokenization on the sentence or like a word level. And then also some of the tagging, that's pretty common, right? And after that, you have some real NLP task, which let's say it's the entity extraction. For example, you want to extract all the people mentions from all documents. And then you send the result to the applications, right? Is that results can be sent to a data, result storage to be used in applications, things like that. So if the task is like that, that's what I mean. It's like a very relatively like a well-defined task, right? You have a fixed input and output, and your document level task can be a machine learning based model. And then you have the standard procedure that you put something in and you get something out. And then data scientists can really just like focus on how to improve that entity extraction model and then deliver the model, and then that's done, right? The remaining is engineering job. But this is actually not super powerful though. So a lot of times you can actually add a little bit of complexity in there. And that's often actually required. And when you have that, you actually make the whole pipeline task a lot more powerful. So for example, it's the same text corpus and you do the pre-processing, and then you still do the document level task. Like for example, entity extraction on every single doc, right? But on the other hand, you can have another type of task. That's a corpus level task. For example, you build a document to document relation graph just on all documents. And then after that, you can actually combine the document level task results with the corpus level task result, and then send to a downstream to do some entity linking and all these things. So if you do these kind of tasks, and you can actually do something that's if you just simply do it on the document level, it may not be actually possible. Right, but if you expand your level to a corpus level, or even just like beyond the corpus level. So for example, if you have some other extra data set like Wikipedia that you can link to, and that's some like extra tasks you can do. And you actually need to do all these tasks in parallel, and then get the result together and then feed into the downstream tasks, and then do the downstream. So in this case, there's actually a little bit complexity here. And a lot of times the hard part is not really about the, all these tasks itself. It is about these tasks are not really fully just independent to each other, right? So a lot of times your accuracy, it's no longer like the single task that all you care is about how the entity extraction perform. Because if you actually care about the downstream task performance, you actually worry about if there's any interdependencies between how you do the entity extraction versus then combine together with how you do the corpus graph. And a lot of times you can have these tiny bits here and there. And it is actually important for data scientists to be involved end to end. So for all these red arrows, for these dependencies, you cannot just simply say every block is a model. I just deliver it to engineer and just let it engineering and take care of it, and you just forget about it. That's not going to happen. And a lot of times, data scientists also needs to be involved in these red arrows to make sure these tasks got combined and computed, and is also has consistent performance all over the way end to end. So this is actually become harder because now you have some complexity in your pipeline, and also your text corpus can actually have different size, depends on the problem you're dealing with, and it can significantly make the data science pipeline too long, and your testing and developing can be a problem there. So how Rick can help here, right? So, and I think, let's just be honest here. Like for most of the, for many of these data scientists, writing good parallel computing code is still generally hard. That's just a fact. And especially like you have data scientists in different levels. And in the old days, a lot of data scientists are really senior people with a lot of computer science background. That actually makes tax, makes it a little bit easier there. But on the other hand, a lot of, if you think about junior data scientists or data scientists from more like science background, like physics, math, chemistry, bio, and they generally more comfortable in the Python ecosystem, and they know how to do these tasks, and they have good understanding of the algorithm. But on the other hand, they do have less knowledge in distributed computing, right? And a lot of times, you know, if you go to the engineer, all the engineering part, and they were people would talk, you know, ask to say like, why don't you just use these kind of tools, right? And it can be like, why don't you use a queue and to actually do the parallelization? Why can't you just use all these fancy tools here and there? Or why can't you just do your you know, multiprocessing? Or actually, why can't you just use some software and define a DAG and then run a DAG and all these things? And the fact is, a lot of data scientists feel like there's a steep learning curve there. And because that's just not their expertise there, right? So they know about algorithm and all these things, and they know if there's like a well set up like software package, for example, if there's some internal mechanism in TensorFlow and PyTorch that can allows you to do things in a distributed way, they can use this right away. But if you require them to do a more complicated task in parallel, that's just generally hard. And there's actually a gap between experience and production. So if you let data scientists just run these experiments in their own way, and they can be slow, and also if they deliver these things because of the interdependency I was talking about, and they can actually bring things to engineering, and then later found that the overall performance is actually bad, and then you could go back, and then there needs like multiple iterations, and it slows down development. And this is why I say like some of time, in many cases, these like end-to-end involvement of data science scientists are actually fairly important. So I think Ray here is really, you know, it's enable a faster iteration of data science experiments, and it allows a larger scope of testing during the development. So data scientists can actually have a more complex pipeline and just write functions as their usual Python functions. And then you just add some, and you can just execute the function kind of like end to end. And then your model is not really simply just a model that's like a TensorFlow or PyTorch model that you deploy. And your model can actually include some of the rules and some of the, you know, very customized rules in it. And you can actually, the whole chunk can actually be delivered to production. And that's actually not crazy at all. So let me go back to this, right? So this is the same pipeline I showed before. And here you can see, if you look at some of the blocks, right? Each block can actually be parallelized in its own way. So for example, data pre-processing and document level tasks, they can be parallelized on every single doc, right? But the corpus level tasks is probably not. It's you actually need to grab all the docs, but you are building a graph, so you probably need some parallelization actually on the graph building, and you know, and you can have some parallelization on your matrix operation and here, right? And then these tasks, when they finish, they got combined and sent to the downstream task. And downstream task may be actually parallelized in the ways that you need to do some resolution or linking on each subgroup of documents, right? So each block can be parallelized in its own way. And traditionally, you can see there's actually a DAG here, and people may say like, hey, you can actually just define a DAG and run it. But like I say, and oftentimes these actually requires extra tools and learning and a totally different way to actually organize and write your code. And that can actually be a problem for data scientists. On the other hand, data scientists here, you can actually just use Ray to write Ray remote functions for each single chunk, right? So you can have just a single like function that do the pre-processing for every single doc. Your input is a single doc and you do things. And then you just put Ray remote here. And you also have the, you can have the Ray remote function on every these subtasks, just write and just get these all written in simple Python functions. And then later you can just execute the whole pipeline. And then you can actually do this experiments on a lot wider range of documents, right? You're not limited to 100 documents or 1,000 documents testing just on your local machine. And you can actually just easily go to a larger node, and you can actually test like 1 million documents. And you can just adjust your resources and get a result faster. And on the other hand, if your resources is very limited, you can just simply still run things in the, these functions are still actually just Python functions. And you can still even just run these things in a, serialized way. And if you don't even, want any parallelization. And if you just want like an easier debugging, like step by step, and understand what's going on in every single step. And that provides some flexibilities here. And the data scientist can actually get own the whole thing like end to end and get the results. So I talked about this a little bit, but just want to emphasize a little more here. And I think the run these experiments in a larger scale is actually very important here, because often what happens is, like I say, especially if you're a junior data scientist, or if you're like a data scientist that from different backgrounds, you may be actually more comfortable just running small scale tests locally, right? So you random subsample the data, and you just run your experiments on a small subset, and you just try to get things work. And then after you feel things works, and then you push to a larger scale, right? And then, for example, sometimes you will have to go to larger scale to be able to actually identify some of the problems. So this is like a real example we had before, and which is you can have some like in natural language processing, you can have some like very rare characters, or emoji characters, or like very weird Unicode. And you don't really bump into it only like after you run actually like tens of thousands of documents, because it can easily slip through when you actually only subsample aggressively on a data set. And that's actually a problem. So if you do this, if you do it locally, everything runs fine. And then you go to the next level and you deploy it in a more engineering fashion, and something fails, and then you need to go back, and these iterations can actually take a time to do. But on the other hand, if you have relatively consistent way to do it on the smaller scale and the larger scale, that's actually makes things easier. So data scientists can actually own the process, and they can actually just simply do it on their local machine first, and then push to the larger scale on the small cluster and run on like 1 million documents. And that will help them to capture all these errors earlier. So you don't need to wait until all the way to deployment to actually identify these issues. So, and also, like I said, because of the interdependencies, sometimes are really inevitable in some of these tasks. So being able to run these things end to end, to testing these things in scale, can be very beneficial for many of these tasks. And yeah, so besides that, there's one extra point I want to make, which is at a company like Primer, and also my current company, and I think many of these startups, or just even mature companies that you actually serve enterprise customers. So it is very often that they will require on-premise deployment. That's you cannot avoid that. So this is true in if your customers are like large corporations, or like government agencies, or healthcare institutions, and that actually happens a lot. And also when you go on-prem, the thing is like, so this may not actually apply to the consumer applications, but this actually applies to many of these enterprise customers. So, and when you go on-prem, the requirement you get and the availability you get is actually really wide range. And here I just list some random points. We actually got these kind of similar requests. These are like kind of like a real life request you will see. And some people may say like, you can get the largest instance ever, and we don't care. But we really have these things. We need to get it processed process like as soon as we can. And we care about latency. We want this right now. And but you can go to another like customer, they will say like, you know, we're okay with running the pipeline just like overnight, and let's just save some cost here. And if it takes like a few hours to run a pipeline, it's okay. And you can go to some of the places, say, do you have GPU available? And they say like, no, but how about we give you a really large node instead, and you can just use that. And you can get all these like very random and wide range resources. And I think this actually present a challenge here about, you know, and how you can narrow the gap between how data scientists actually running these experiments and how you may actually need these things to be done in production. And you know, if your production system is you know, too far away from your experiments, and the problem is like your iteration is just long, and you often like, you know, you later you will have all the way down and you see some production problem, and then you need to go all the way back to a data scientist, and that iteration sometimes it's just like kind of unbearable in that way. Yeah, so that's all the I think these are all I'm gonna talk about today. It's more about just present some of the real life pipeline, and how some of the problems can get complicated, and how some of the challenges that we often facing, and when we actually need to serve enterprise customers, and how Ray can actually help here to narrow the gap between these experiments and the production. And that's it. Thank you.